Welcome back to the Foundry by Forge College. Today, we're jumping right into a brand new explainer on the actual real-world costs of finding data in Cloudbreak. And, when I say costs, I'm talking about the time, the money, and the raw computing power it takes to keep this whole thing running smoothly. Now, in our previous explainer on partition lookup and access patterns, we figured out how to locate our data. But today, we have to look at the flip side. Because sure, you can find your data, but what is it actually going to cost you when you scale up? We're going to put these architectural decisions under the microscope and see exactly how they impact the bottom line of a massive system like Solana. So let's dive into this. We know how to locate partitions, right? But what happens to our system when we start factoring in the really heavy lifters, sustained throughput, tail latency, and that sneaky, often invisible storage overhead? Look, it's pretty easy to design a system that works flawlessly for one user asking for one tiny piece of data. But what happens when millions of requests are just flooding in every single second? Suddenly, every tiny little inefficiency multiplies. A microsecond of delay here, a couple kilobytes of extra storage there, and boom, you've got a massively expensive, sluggish system on your hands. Today, we're going to learn how to measure those exact trade-offs so you don't get caught off guard when the bill comes. Here's our blueprint for today's explainer. We'll start with the cost of partitioning, move into the library metaphor, then measuring latency and throughput, followed by storage and rebalancing costs, and finally wrap up with operational runbooks. Okay, Section 1, the cost of partitioning and the trade-offs we face in Cloudbreak. The absolute biggest takeaway when diving into these structures is that there are no perfect solutions in distributed systems. None. There are only trade-offs. We're constantly playing this high-stakes game of tug-of-war between speed and storage. To really wrap our heads around this push and pull, our core mental model for today is what we call the library metaphor. Imagine we've drawn out a crisp engineering blueprint in dark green ink, and in it, Cloudbreak's entire dataset is a massive city library. The partitions, those are your physical bookshelves. The metadata cache is the central card catalog sitting right at the front desk. And every single read or write request is basically a highly caffeinated librarian physically sprinting to a shelf to fetch or return a book. Keep that exact image in your head, and the complex math we're about to do is going to make total intuitive sense. Section 2, the library metaphor. Shelves, catalogs, and librarians. All right, so here is the central dilemma. Let's say we decide to use coarse-grained partitions. In our library metaphor, this means we've built these massive, mile-long bookshelves. The upside? Our central card catalog is tiny and super easy to check, but the downside is huge. Once our poor librarian actually gets to that giant shelf, they have to spend a ridiculously long time sifting through thousands of books just to find the right one. Now let's flip it. What if we use fine-grained partitions? Now we have millions of tiny little shelves. Once the librarian finds the shelf, boom, grabbing the book is instantaneous. But the card catalog at the front desk is now the size of a football field. Your librarian ends up spending all their time just trying to look up which tiny shelf to visit in the first place. You see, you fix one bottleneck and you immediately create another. Moving on to Section 3, measuring latency and throughput, the physics of the library. It's time to step out of the theoretical world of our library metaphor and enter the actual physics of the system. We don't pay our infrastructure bills with metaphors, right? We pay them based on hard performance metrics. And it turns out latency isn't just one monolithic number. It's a compound metric made up of a few key pieces. First, you've got LLookup. That's your metadata lookup latency, or the time spent checking the catalog. If your metadata cache is cold, meaning the data isn't loaded up in fast memory, that number is going to spike aggressively. Next is L-partition, the per-partition access latency, essentially searching the shelf. If you chose those massive coarse-grained partitions we just talked about, L-partition is going to severely penalize you. Finally, you add an L-proc for processing and L-network for the data transfer time. If you want to fix a slow system, you have to discover exactly which of these four components is bleeding your time. Now, let's talk throughput. In a perfect theoretical world, your aggregate throughput is simply the number of partitions multiplied by the requests per second that each one can handle. But there is a massive warning label attached to this. Skew collapses gains. What does that actually mean? Well, imagine you have 1,000 librarians ready to work. That's huge theoretical throughput. But what if a massive NFT drop happens on the network and suddenly 80% of your library patrons burst through the front doors fighting over the exact same book on the exact same shelf? That right there is a partition hotspot. And frankly, it doesn't matter that you have 999 other librarians standing around doing absolutely nothing. Your throughput hits a massive traffic jam simply because all the demand is skewed to one single spot. Section 4.
Storage and rebalancing costs, the price of remodeling. As you keep exploring courses across the Forge College community, you're going to constantly see that storing metadata and moving data around incurs a really heavy operational tax. Think about it. Every single partition needs a header, just a little piece of metadata identifying it. Now, a 4 kilobyte header seems completely harmless, doesn't it? It's tiny, but multiply that by, say, 250,000 partitions, and suddenly you've got 1 gigabyte of memory overhead just to hold the catalog. And remember our hotspot problem from a minute ago? Let's say you decide to fix those traffic jams by splitting your data into a million tiny, fine-grained partitions. Well, congratulations, you solved the hotspot, but now you suddenly need 4 gigabytes of highly expensive memory just to hold the headers. This is exactly how a quick solution for latency can absolutely explode your storage budget. And heaven forbid you actually need to change your shelf sizes while the system is actively running. Rebalancing the system costs you heavily in state copying, global metadata updates, and massive input/output contention. Let's go back to our library. Imagine trying to remodel the library, literally tearing down shelves and building new ones, while your patrons are still actively inside asking for books. It is incredibly painful. Moving 500 gigabytes of data at a rate of 500 megabytes a second takes over 16 minutes. That is 16 full minutes of massive background interference, where your standard everyday read and write requests are essentially fighting the remodeling crew for bandwidth. So, how on earth do we survive this rebalancing act? Well, engineers usually rely on one of 3 architectural strategies to reorganize the shelves without shutting down the entire building. Strategy 1 is snapshot and copy. It's incredibly safe and consistent, but it demands double the storage space temporarily. Strategy 2 is incremental streaming. This one is much kinder on your peak bandwidth, but keeping both the old and new sides perfectly reconciled and accurate while they stream, that's a massive headache. Or Strategy 3, virtualization. Basically, you just put up a sign that says, moved to aisle 5. You save on copying right away, but you make the librarian's lookup paths much more complicated. Every single strategy has a painful cost attached to it.
Which brings us to Section 5, Operational Runbooks, Rules for the Head Librarian. With all these intense trade-offs, the hotspots, the memory spikes, the remodeling headaches, how do we actually manage the chaos? Well, we definitely don't rely on intuition. We use strict operational runbooks with hard thresholds. For example, if the queue depth, meaning the line of patrons waiting for a shelf, goes above a certain variable X, we automatically trigger a partition split. If our background migration bandwidth drops below Y, we immediately pause the remodeling because it's starting to interfere with live traffic. If our cache hit ratio, the amount of times the librarian already knows exactly where the book is, drops below Z, we allocate more memory to the catalog. We're not guessing here. These rules convert all of our architectural trade-offs into repeatable, data-driven decisions that automatically balance performance against cost in real time. And that brings us to the ultimate goal. Designing data structures for a system like Cloudbreak is just an incredible game of constrained optimization. The real challenge is to meet a target P95 latency, meaning you're making sure 95% of requests are lightning fast while maintaining massive throughput, and doing all of that while keeping your metadata footprints and migration bandwidth strictly within a tight financial budget. Every single design change has to be evaluated with workload-shaped simulations to ensure that fixing your median latency doesn't accidentally explode your operational costs. So knowing all these heavy trade-offs, the steep latency costs, the expanding memory footprints, the delicate balancing acts, how exactly does Cloudbreak take these layout choices and turn them into massive, practical advantages for the Solana network? Well, that is the million-dollar question, isn't it? And it's exactly what we're going to cover in our next explainer. But that wraps up our time for today. I highly encourage you to visit forge.college to learn more about this subject, dive way deeper into these Web3 topics, and join our learning community. Thanks so much for joining me, and I'll see you in the next one.